All right, guys, welcome. We're going to be starting our CCNP Enterprise Core lecture, and in the first section, we're going to be talking about kind of what Cisco defines as their approach to enterprise network design, examining Cisco enterprise network architectures. It's very similar to kind of the traditional approach to campus design that Cisco has pushed for many, many years, the core layer, the distribution layer, and the access layer. But what they've done, and we've seen this in some of the previous content as well, is what they've done is they've decided to kind of compartmentalize the functions of an overall enterprise network architecture to include things like the campus core, the campus edge, the service provider components or the service provider elements, remote locations, etc. And we still kind of incorporate the whole idea of core, distribution, and access, the core layer being, of course, the backbone, if you will, of the enterprise network, the distribution, which is kind of the aggregation point, the policy point of the network, and then the access layer where all of our endpoints connect and so on. So that's what this particular section is all about. Discussing those different elements in this model. So you can see kind of an image here or a graphic that kind of breaks up these different components or these different elements, and it recognizes essentially the functions of a network based on or the compartments, if you will, of a network based on their particular function. The campus is what we traditionally would have talked about in maybe a CCNP routing and switching course where you had your traditional core layer, distribution layer, and access layer. We see that kind of depicted here. This kind of teal box or light blue box would be my core. This middle box here would be my distribution layer. And this dark blue box here would be my access layer with redundant connections and maybe some routing. Switching at layer 2 at the access layer, maybe some routing and so on at layer 3 and the distribution layer, and then the core layer, high-speed routing as well. And we would have some redundant connectivity to the data center or other campus modules that might exist besides just the data center module where we'd have our server farms and so on. The internet edge component, if you will, that would be where we would apply security elements or security components, web caching, policy-based decision processes that allow us to secure access to our internet service provider or our telecommunication service provider. We may have some sort of remote worker connected to the ISP as well, and that remote worker could connect through, say, an SSL VPN over the internet. It wouldn't be more of a private internet, it'd be more of a remote access or site-to-site VPN type thing. We might also run over this ISP connection. We see a branch office here with a firepower firewall and some other core distribution and access design at the branch office. So we might be running something like a customer-owned VPN over that type of connection, using something like a DMVPN or GetVPN's connection. The WAN edge is different from the internet edge in that the WAN edge is usually going to be connected to some sort of service provider managed VPN, like an SD-WAN or MPLS type of network. But it's some sort of privatized virtual private network that allows us to connect to various branch offices and so on. So, oops, sorry about that. Got the slides all messed up there. But that's what they kind of discuss here in the text here, right? The enterprise campus. That's going to focus on providing your enterprise services like DHCP and DNS and file services and database services and application services that you would typically see within the campus network itself. Could also include things like converged access, unified communication, the standard services that you would see within the enterprise network itself. Typically, we're going to use some sort of routing protocol within this topology as well. an IGP protocol like EIGRP or OSPF. Those are the two most common. We'll have a data center component as well, where we're using some sort of spine and leaf data center design, and you can learn all about that in the CCNP data center track. At the enterprise edge, like I said, that's where our WAN connectivity is. We might have on the enterprise edge some sort of traditional internet service provider connectivity purely for internet-based access, or some sort of customer-managed VPN access, or we could have maybe a multi-protocol label switching connection, Metro Ethernet, Sonnet, etc. on the enterprise edge. Now remember, the enterprise edge can be broken up into a couple of different components, right? This is the module, the enterprise edge module, but we have WAN edge, we have internet edge. There's actually some other components like e-commerce, and sometimes they might even have a remote access module where you have VPN concentrators and so on that are specifically designed for providing that VPN access to that enterprise edge connectivity. And then the service provider edge, again, one of those kind of sub-modules, if you will, that provides connectivity between our primary location, our main location, and our external locations like our branch offices and so on. The remote locations themselves, those would be our branch offices. They might be connected either through a service provider managed VPN, like SD-WAN or MPLS. Those are going to be your most common connectivity options these days. Or it might include some sort of customer-managed VPN solution. Most common these days is DMVPN, which is your dynamic multi-point VPN using GRE and IPsec and other protocols to manage that particular process. All right, some of the key concepts that we need to address when we're building our network, and we'll get into this. Maybe we'll see you guys later on in the design class, where we talk about a network that is self-healing, which means that we have redundancy built into it, not only at layer 2 but at layer 3, by using various protocols that provide for redundant path selection. But we'll also have an option for even redundant paths, redundant connectivity. It's going to involve the use of different protocols like first hop redundancy protocols, of course the spanning tree component, as well as virtual routing and other elements that make the architecture redundant. Self-defending, meaning that we have advanced dynamic security elements that are built into this as well. Self-optimizing, so we're running intelligent protocols that allow the network to make its own decisions on the best way to communicate and the best way to route traffic or switch traffic across the enterprise. And self-aware. That's where the programmability aspect comes into play when we talk about self-awareness. But really, it's kind of more of a generic term to describe all these other elements that we're adding into the enterprise. When we look at overall enterprise network design, there are some things that we need to take into account. Right? Scalability is always one of the primary components that we consider when we're trying to design a network. We want to make sure that as the network grows, the technologies that we're implementing today are going to be the same technologies that we're going to have an opportunity to maintain and keep as we add more services to the network, as we add more users to the network. We want to make sure that that network is going to scale. So we need to choose protocols and architectures that are conducive to that type of environment. Also, wireless has become kind of a huge element in most enterprise designs these days, because wireless technology has advanced so far that oftentimes the wireless connectivity is going to be more efficient and even faster than traditional wired connectivity. For example, we're seeing in 802.11 AC Wave 2 that we have speeds upwards of 1 to 2 gigs, and with the 802.3 Bravo Zebra standard, 2.5 to 5 gigs and so on. Now, if you think about what your traditional switching architecture looks like, at least from a desktop or endpoint perspective. You're not getting speeds of 2.5 to 5 gigs on an endpoint. You're getting maybe a gig, and in some cases, for more kind of higher demand environments, you might get some 10 gig connections, but it's not very practical to have that going to your desktops. So there is a technology Cisco's had for quite a few years actually called multi-gig. On our YouTube channel, we have a video about that multi-gig technology. It's pretty interesting. Taking Cat5 infrastructure, Cat5e, Cat6 infrastructure, primarily Cat5e, and traditional switched architectures, and being able to push 2.5 to 5 gigs over that infrastructure to support things like advanced wireless solutions that we see today. It's pretty interesting if you go out and check that out. It's Cisco has their own TV station, and they publish a lot of these new technologies through that TV station, and we post a lot of those videos on our YouTube channel. All right. So as we look to deploy all this different technology, everything is now integrated. We've got virtual desktops with a back-end virtual architecture. We have remote access components. We have access points. We have security systems. We have Internet of Things elements. Everything is automated and integrated into the network infrastructure. So now when we come and we start to design our infrastructure, we need to consider not only QoS, quality of service, to ensure that everything is being, all the traffic is being handled appropriately. We need to make sure that we have the appropriate power to provide power to these endpoints, up to 60 watts per port, it says here. That's pretty high, but a lot of the devices now do require quite a bit of power. And the new Catalyst 9000 series switches, they're actually capable of delivering about 100 watts per port, which is good because we have different classes of PoE devices, and each of those classes are going to require different types of power. It's not just our IP phones anymore. It's security cameras. It's other access devices that we might have on the network that provide access to the network itself, or at least provide some sort of service on the network itself. We have to be, of course, concerned about security. We won't get into it in as much detail in this class. The CCNP security, of course, covers this quite a bit. But things like Cisco TrustSec, we're using security group architectures, using security group tags and asset security. To be able to identify not only who's connecting to the network, where their attachment point is, and then based on that attachment point, we can assign a uniform security policy to those endpoints so that the security policy becomes dynamic. And we push out downloadable ACLs, or we do some dynamic VLAN assignments, or whatever it might be through the use of Cisco ICE, the identity services engine that Cisco has. And it provides us the ability to automate, in essence, our security architecture. Traditionally, that would be something that would have been configured statically, but that's changed over the years. They mentioned MACsec here as well. In fact, I saw a question on the exam related to that. MACsec is a layer 2 encryption mechanism that does wire-based encryption between switches and devices. So you will, the switch, of course, will have to be able to process switching information that's unencrypted, but before it sends it onto the wire, it will encrypt that information, send it onto the wire encrypted, and then once that information reaches the next device, it'll be unencrypted or decrypted so that the switch and the receiving switch can process that information. So we're talking about basically physical security over the twisted pair Ethernet cables or whatever we're sending our traffic over. Network analytics is pretty important as well. Technologies like NetFlow, SNMP, those types of things, what we refer to as network telemetry, are going to be important. The Internet of Things, like I mentioned, everything is connected to the network these days. So we need to be aware of that. We need to have pretty high bandwidth connectivity as well, because now that we're pushing 2.5 to 5 gigs of traffic through maybe an individual port, our uplinks and our links to our data centers, the links between our distribution layer switches and our core switches, we're now talking about implementing speeds of 40 gigs and above. Right? Traditionally, it was always a gig, or maybe we had some sort of ether channel configuration where we were bonding multiple links together to get some sort of aggregated throughput. Now we're really pushing, beyond 10 gigs, 40 gigs up to 100 gigs across these various links. So we have to have platforms that can support that, and it's still data. I mean, it doesn't change the underlying protocols that we're going to use to facilitate that communication. But, we still have to have the physical connectivity to support that. So we need to make sure that we choose platforms that are going to meet those needs, right? Towards the end of the class, we'll be talking about the DNA, Cisco, what we call the digital network architecture. That's basically Cisco's automation architecture. Right, Cisco DNA is kind of incorporated into all of the modern Cisco platforms. There's DNA licensing that you purchase to go along with the platforms that you're implementing. Most of the modern platforms are going to include DNA. I mean, they don't include it. You have to pay for it, and it's kind of expensive, but that's what provides you that programmability aspect. One of the questions that I often get from students, particularly in the CCNA, is, well, if I'm doing all of this software-defined networking and we're using Cisco DNA and we're using APIC-EM and ACI fabrics and whatnot, how is that changing my role as a network engineer, right? Do I need to understand EIGRP and OSPF and spanning tree and ether channel and all these other technologies? And my answer is always, yes, you need to understand those technologies, because network automation doesn't get rid of those technologies. It just provides you the ability to automate the configuration of those technologies. So you still have to understand how those technologies work. You still have to understand their function. You may have to troubleshoot and so on. So just because you have SD access or software-defined access, it doesn't mean that you're getting rid of all of those technologies. You're just you're incorporating tools to orchestrate aspects of configuration, if you will. So onboarding clients or onboarding employees, segmenting the network based on security policies, integrating IoT elements in the network, providing some sort of contractor access to the network or guest access to the network. SD access just allows us to automate our policy decisions without having to go into the individual command line interfaces and configuring those elements separately, right? And all of the underlying architecture, the Python scripting, the programming languages that we talk about in the SD aspect, those are just the open standard applications that allow this programmability to be projected to the devices themselves, and allows you to push out these configurations to the devices themselves. So it's still important to understand the individual elements, if you will, of the underlying technology. You still need to know about EIGRP and OSPF and so on. So SD access is what we would is the software-defined element that we would apply in the DNA architecture to our enterprise core, if you will, or our enterprise module, our campus module. For the wide area network, the SD-WAN element is a way for us to apply that programmability to provide scalability and open architectures to our WAN, right? Our cloud-based solutions. So we can use things like Cisco vManage Console, to create this overlay fabric to connect all of our various locations, right? Our data centers, our branches, our campuses, our facilities, and so on. All right, so at the bottom of the screen here, you can kind of see what Cisco defines for each of these elements. The enterprise campus that represents geographically distant parts of the enterprise network. I would say enterprise campus, yeah, it's defined as distant parts, but enterprise campus is really your core network, right? That's what you have within your architecture, your campus architecture. So I don't know how distant they're referencing, the distance that they're referencing there, because to me that that term kind of denotes that these are geographically dispersed elements, but it is your campus, right? It is the network architecture that you have. The enterprise edge, those are the submodules that provide internet connectivity. And like I said, there's multiple types of submodules that would exist. The service provider edge would be one of them. The where you have your ISP connectivity. The WAN edge would be another one where you might have a service provider managed VPN, an e-commerce edge component as well. If you have some sort of e-commerce application, remote access edge, where you might have some sort of VPN concentration for remote workers or teleworkers and so on. And then finally, your remote locations. And these remote locations could be connected in many, many different ways. All right. So what are some of the design fundamentals that we have to take into account, right? It depends, right? It depends on the size of the network. It depends on what the growth requirements are for that particular network. Are you designing a campus that includes only one building, maybe one floor, maybe it's a fairly small network, or is it a very large enterprise network that's going to incorporate or require the use of a more advanced design? Maybe you're using a spine and leaf design in OSPF to scale the network, and you're moving away from EIGRP, which is mostly a flat design. It just depends. There are some elements that kind of get incorporated in all of these designs, and then there are some elements that would change depending on the type of architecture that you're trying to design, right? Is it a few hundred connections, or is it thousands of connections? Do you have, say, lots of VLANs? Do you have a large need for security and so on? A flat model, which we see depicted on the left here, is pretty straightforward. It's basically a layer 2 network, a single broadcast domain. Maybe you might have a couple of different VLANs to segment the network into multiple broadcast domains, but overall you're running the network as basically a flat architecture. You're doing a lot of switching and very little routing. And again, this doesn't have a whole lot to do with the security piece. We'll get into the security stuff a little bit later on, but as the network grows, and as you add more and more endpoints, as you add quality of service, as you add other services to the network, you may look at a hierarchical design. Not only in the physical design, which we see here. I mean, we've got our traditional core here. This is the core network. This are the core of our network. This is the distribution layer. This is the access layer. Internet edge probably would not be directly connected to the core, but we have kind of this hierarchy, if you will, and each of these layers provides a specific function. And that's obviously what we're going to be breaking down in this particular section here. But it's not just a matter of physical design. We have our access layer switches, which are connected to the distribution layer switches. It's actually not really drawn correctly here because these access layer switches would have redundant connections to each of the distribution layer switches, much like you see here between the core and the distribution layers. Because we want that physical redundancy, right? If one distribution layer switch fails, I don't want those access layer switches to lose their connectivity. How you decide to do that will depend on what kind of resiliency you want in your network, what kind of protocols you're running in the network, whether or not they're going to require some advanced design and so on. All right. So it really depends on a lot of different considerations. All right. The with regard to what protocols you choose in the enterprise, with regard to the physical architecture that you decide to implement. And as we break down these protocols, I'm going to be teaching you guys, what protocol I would choose for what, and why I would decide to do that. All right. So let's talk about this 3-layer model and this hierarchy, if you will, and talk about what each of these layers are used for. All right. So it says here the hierarchical model allows you to design the internetworks in layers, and that's true, right? We only have 3 layers, but they reference the OSI model here, which we don't really talk about too much in this class. But by breaking up the function of a network, or by breaking up the programming or the configuration and the function of each of these layers, we can, in essence, kind of isolate any faults in the network. It makes it easier to troubleshoot the network if there are issues. And it actually adds for 2 things that are really critical in any network design. Probably the 2 most important things when you're designing a network, and that is convergence and scalability. How does the network react when something happens? How does the network react when there is a change in the topology? If there's an issue with a configuration, how quickly does the network respond to that particular issue? Whether it's rerouting traffic over a different link, or a physical device taking over in an active-active failover pair, or whatever it might be for high availability. The other element that's really critical to design is scalability. And without a core, they used to have a diagram that would describe this, but without a core in your topology, without a distribution layer, scalability becomes a real difficult thing to achieve because the network is flat. You have very large broadcast domains. Traffic flow is very inefficient, etc. So that's something to consider when you're doing this design. Now, each of these layers that we see here, between the core, the distribution, and the access, they each have a very specific function, right? The access layer, that's where you're going to have all your end user services, right? Power over Ethernet, VLANs are extended to this layer, traffic classification, traffic marking is extended to this layer if you're doing quality of service. You might be pushing out downloadable ACLs or port-based ACLs to the ports. You might be doing 802.1x, for example, at the access layer to do network-based authentication. Power over Ethernet, I think I mentioned that one already. All kinds of things that they're going to be end-user facing, in other words, right? Traditional elements that you guys see all the time. So the access layer is kind of that front-facing layer that everybody gets all their services from. Probably the most common question that people have, and we'll talk about this when we get into the VLAN section, the most common question people have about the access layer, because we know we're going to do things like power over Ethernet. We know we're going to do probably some sort of QoS traffic, queuing, possibly some ingress queuing, egress queuing at the switch ports, but certainly classification and marking will happen towards the edge. Well, that's where our trust boundary will be extended to for QoS. And we're going to be providing, basic connectivity services like, VLAN assignments, broadcast domain allocation based on the VLAN and so on. But we might also be providing other services like 802.1x. But like I said, one of the biggest questions that you would probably see with regard to the access layer is, am I going to run a layer 2 access layer, or am I going to run a layer 3 access layer? Am I going to route to the edge, or am I going to switch at the edge? And we'll talk about that more as we get into the VLAN discussion a little bit later on. You'll see that and what are the pros and cons of each of those choices. But by definition, what it says here in the book is the access layer is used to grant user access to network devices. In a network campus, the access layer generally incorporates switched LAN devices with ports that provide connectivity to workstations and servers. In a WAN environment, the access layer for teleworkers or remote sites may provide access to corporate networks across WAN technologies. We don't typically use, I don't typically use the access layer term to describe WAN connectivity, because usually it's going to involve some sort of routing, some sort of security component, but it can be done, right? So it makes sense. Client access, all the client services are going to be at that layer. The distribution layer, though, this is the workhorse. The distribution layer is the one that's going to be responsible for policy enforcement. Routing is going to occur at this layer. Typically, QoS policy enforcements are going to happen here. So we're going to have our congestion management, things like low latency queuing, priority queuing, class-based weighted fair queuing. We're going to have things like security enforcement as well. So we might have access control lists applied here. We might have other security elements like VLAN filters applied here as well. Anything that has to do with overall policy decisions, including routing decisions, by the way. This is where our routing layer is. So EIGRP or OSPF, we might have our OSPF hierarchy, spine and leaf hierarchy that's deployed here as well, with area 0 and our non-area 0 areas and so on. By definition, it says the distribution layer aggregates the wiring closets using switches to segment work groups and isolate network problems in the campus environment. How does that segmentation occur? It occurs with VLANs, right? Routing. Similarly, the distribution layer aggregates WAN connections at the edge of the campus to provide policy-based connectivity. So I call this the workhorse layer because it is basically the layer that is responsible for all policy decisions in your enterprise. This is where all of the primary configuration elements come into play when it comes to policy decisions in the enterprise. Then we have our core layer, which they refer to as the backbone. Actually, the core layer is predominantly, in most cases, going to be providing only one service, and that is high-speed routing, transporting data from point A to point B. In fact, in a lot of cases, they will tell you don't make policy decisions at the core. Make all your policy decisions at the distribution layer and rely on the core for transport only. High-speed switching, high-speed routing, delivering data from point A to point B as quickly as possible. So all of our policy decisions have already been made. All of our QoS decisions have been made. All of our security decisions have been made at the distribution layer. We're just basically trying to get traffic as quickly as possible from point A to point B. Now, in a lot of cases, and they don't mention it in the book here, I don't believe, but in a lot of cases, a lot of organizations will choose to do what we call a collapsed core design. They don't have a budget, or they don't necessarily have the ability to, or the resources, if you will, to have a separate core and separate distribution layer. So a lot of times you'll see the core elements and the distribution layer elements combined together in, say, an aggregation switch or so on. You know, like a 9000 series switch, or maybe a Nexus switch, like a 5K or a 7K or something like that. So there isn't always this kind of distinction between the core and the distribution layer. A lot of times you'll see those combined together. But if you have the budget and if you have the resources and the requirements, you can separate those functions. One of the other things I mentioned, of course, is what is the difference between a routed architecture and a switched architecture. There are a lot of considerations to take into account when you're dealing with this design choice, right? Switching at the to the edge of the network is very traditional. That's typically what we would see in most designs. We have VLANs that are created and managed at the distribution layer, And then we have those VLANs that span across multiple buildings, across our campus at the access layer. The problem with having a layer 2 edge or a layer 2 access layer is that you have to design in spanning tree. I mean, you always have to have spanning tree, but with a traditional layer 2 design towards the edge, spanning tree becomes a really big concern. And you have to, of course, marry your first hop redundancy designs to your spanning tree designs to make sure that the topologies correspond to each other, they match for convergence reasons and so on. We'll get into that when we get into each of these individual protocols a little bit later on, right? But we always do routing at the distribution layer. That's always the case. It's just a matter of whether the VLANs span the entire campus or whether they're isolated or localized to a particular switch. The bottom diagram there, you can see we've kind of extended layer 3 all the way to the access layer. Now the benefit of that is everything is routed and practically nothing is switched. Generally speaking, routing is a little bit easier to troubleshoot. We can certainly control the size of our broadcast domains, but the downside is our network becomes a lot more complex. Why is that? Because now we have layer 3 networks everywhere. So for every VLAN, we have to have a different subnet, and instead of having one voice VLAN that spans multiple layer 2 switches, we have a separate voice VLAN for each switch. So on the top diagram, you might have one voice VLAN that spans all of those 4 access layer switches, but on the bottom, we would have to have 4 separate VLANs, each providing the same function, voice over IP, but different broadcast domains. So there's pros and cons to each of these, and we'll get into the details of that as we start to kind of go into depth in some of these other designs as well. All right, let's just see what it says here in the book. It says the first option is to have only a layer 2, known as bridging at the access layer. The VLANs are terminated at the distribution layer. We mentioned that. And half of the uplinks might be blocked because of spanning tree. So that was what I was discussing previously. Spanning tree is a huge design consideration in that case. The second option is layer 3, which is known as routing to the access layer. The VLANs are terminated at the access layer devices, and then the links between the access layer and the distribution layer are all routed links. As you can imagine, that makes your layer 3 architecture much more complex because you have to do routing, which is a lot of subnets, a lot of things that you have to manage from a layer 3 perspective. So it can make it a little bit more complicated in that regard. All right. A layer 2 only access design, very traditional, much cheaper, but because spanning tree, because you have a lot of redundant connections, spanning tree becomes a really big thing that you have to deal with. In a layer 3 design, like I said, a lot of planning required for IP routing and subnetting and so on. All right. So which of the following is true regarding a flat network design? A flat network has multiple subnets. All devices in the subnet have dedicated bandwidth. All devices are in a different broadcast domain. A broadcast packet is processed by all the devices and uses CPU time on each device in the broadcast domain. It would be the last option, wouldn't it? Right? It would be this option here because a flat network means a single broadcast domain, and obviously it's referred to as a broadcast domain because if a broadcast is sent, anybody within that network, whether it's an all-ones broadcast or a subnet directed broadcast, all the devices in that network are going to have to process that traffic, and that's going to take up, CPUs and so on that particular device. All right. All right, in a traditional multi-layer campus design, as I said, one of the two elements that we're concerned with are scalability and recoverability, if you will, what I would refer to as availability, right? The ability for the network to recover from failed circuits or failed devices or failed protocols, whatever it might be, right? On the left, we see kind of the collapsed core design that I was referencing. On the right, we see more of a traditional 3-layer design. And again, it really just comes down to resources and budget and design necessity as well, depending on how large the architecture actually is. Will determine whether you decide to use a collapsed core design or not. So the Cisco Enterprise Campus architecture, like I said, divides the network into functional areas. We talked about that in the beginning of this section here. And even though Cisco does define these 3 layers, the core layer, the distribution layer, the access layer, it isn't a strict design requirement, right? In a smaller campus, like I said, a small business or even if you get into a really, really small business where you have 100 users, you might not even have a separate access layer. You might have one 6500 series switch or maybe a Cisco 3850 switch stack that services the entire campus. And so you've now combined all 3 layers together, access, distribution, and core in a single switch stack. So it really just depends on the overall architecture and the size of the network. And sorry about that. So it really just depends on what the overall architecture looks like, right? What it is that you're, where you're implementing the design and so on. I think you guys get the idea. I've mentioned it a couple of times already. All right. Another consideration for the access layer, right? Access layer, of course, is where our devices attach. We've got converged elements, right? Cisco IP phone with a PC attached to the phone. So at the bottom here, we might have an IP phone. So that's going to introduce some requirement for some sort of quality of service where we're doing DSCP and we're trying to mark traffic and classify traffic at the edge, applying some sort of QoS policy at the edge, establishing what our trust boundary is. So at what point do we trust the quality of service markings and what point do we not trust the markings? There's a PoE component, right? The wireless access point, for example, is going to need power over Ethernet. But we also have to consider the devices that are attaching to that access point. How are those devices being authenticated? How is their traffic being attached to the network? Are we using an autonomous design? Are we using a lightweight design where we have a controller when we're using some sort of CAP-WAP tunnel, DTLS tunnel to be able to tunnel the traffic back to the controller and so on. Is there trunking involved, right? Does that access point have multiple SSIDs? And rather than having a traditional access port for the AP, we're going to have a trunk port, which means we're going to be doing some .1Q tagging or something like that. Personal telepresence device, that would be like a video endpoint. Same kind of consideration there. We would have to have some sort of QoS and so on. All right. So there's all kinds of devices that we can connect to the access layer. Those devices are going to have different needs for configuration. They're going to have different needs for communication. We kind of saw these bullet points at the beginning. The network has to be self-healing, right? Traditionally, when we talk about any kind of network design, we want to incorporate the three cornerstones of configuration, which is confidentiality, integrity, and availability. Availability is what they're referring to here, right? This self-healing option. We're running maybe a first hop redundancy protocol. We're running some sort of architecture that allows for failover and redundancy in the event that something fails within the topology, whether it's a router, a switch, whatever it might be, a physical link, and so on. All right. How do we incorporate that self-healing component? We have redundant architectures, right? We might have multiple access points and an access point fails, and we can use radio resource management to do black hole coverage, where we can automate the configuration of the channels that we're using, as well as the power that we're using to manage the wireless spectrum and so on. It could be redundant elements in design, using redundant protocols like spanning tree, first hop redundancy protocols, designing in elements that allow the network to make quick decisions on rerouting traffic or putting traffic over a different link or whatever it might be. Self-defending is the security component, right? And pretty much the primary element that we use for self-defending networks these days is Cisco ICE with the incorporation of 802.1x, where we have when a device attaches to the network, it authenticates itself, the user authenticates themselves, and then based on that authentication profile, we can do a device assessment. We can profile the device, we can do a posture assessment, we can identify what type of device that is, what its current status is, and then based on that information, we can decide how that network is, or how that device is going to attach to the network. We can even do things like remediation and say, hey, you're not going to be able to connect to this network unless you have these specific elements, right? You don't have the right antivirus, you don't have the right definition file, you're not running the right software, whatever it might be. So we're not going to allow you to connect. There's other elements to this, right? You use Cisco TrustSec, we use security group tags. We'll talk about that a little bit later on. That's more of a policy enforcement component. So rather than doing traditional security, static security policy enforcement, we'll do dynamic security policy enforcement using the Cisco TrustSec architecture. We can incorporate things like MACsec as well. All kinds of different things that we can incorporate. Self-optimizing, right? They mention this specifically with wireless a lot, right? We call that radio resource management. Maybe there's some interference that's occurring in the network, and the wireless LAN controller can then go out and reprogram the access points to change frequency, change the channel, change their effective power output, etc. And we call that RRM, radio resource management. But there's other things that we can use in a network design for self-optimization, right? We can use other tools. For example, I might be running OSPF in my enterprise, and I might be incorporating the use of BFD, bidirectional forwarding detection, to optimize the convergence times for OSPF. So rather than just rely on the standard hello and dead intervals for OSPF to identify neighbor adjacencies and the lack of adjacencies, I might incorporate the use of BFD for sub-second reconvergence. And that's part of that optimization. That also goes to the self-healing aspect as well, right? Being able to converge quickly if something changes. And the network has to be self-aware. That's where network telemetry comes into play. We use things like NetFlow, network-based application recognition. NBAR is something that we typically use with QoS. It allows us to identify traffic based on flow patterns rather than static information like port numbers. So I can identify, say, an RTP audio stream, which might use, by the way, you know, completely different ports, right? It uses a whole range of 16,000 different ports. So it's difficult for me to identify an RTP audio stream based solely on the port number. I can use network-based application recognition to identify that flow based on the general characteristics of the traffic itself, right? And then we can apply QoS policies and identify how the users are going to interact with those applications based on identifying the application based on its characteristics, multiple characteristics, by the way, right? Network analytics is very important, being able to provide services that are ubiquitous, right? I want a user that's attached on port 10 on the switch in building 5 to get the exact same service if that user went to building 10 and plugged into port 3. And I want that service to be mobile. I want that service to be automatic. In order for that to happen, the network has to be self-aware. Now, a lot of people, when they hear that term self-aware, they tend to think of software-defined networking. Certainly SD access and SD-WAN provides that, part of that automation for self-awareness. But it's more than that. I mean, we don't have to be running software-defined networking to build in self-awareness into the network. All right. As I mentioned, the distribution layer, that's the workhorse, right? Routing, policies, filtering, security, QoS, redundant connections to the core, redundant connections to the access layer. The distribution layer is the workhorse, right? That's where we're doing all of our policy decisions. Notice in the last paragraph here, it mentions things like first hop redundancy protocols, like the hot standby routing protocol, or gateway load balancing protocol, or the virtual router redundancy protocol. We'll have a whole section on that a little bit later on. Then finally, the core layer, high-speed backbone. All right, very, very fast convergence. No policy decisions at this layer, getting traffic from point A to point B as quickly as possible to ensure that the data is going to be delivered to its destination as quickly as possible. When is the core layer needed? Oh, there's that diagram that I was referring to. This is a design with multiple buildings. Not sure what standard image means, but this is the building, a design where we don't have a core. We simply have a bunch of distribution switches, and for the purposes of optimized routing and distribution of packets across the enterprise, as well as redundancy, you can see that as we add an additional distribution layer switch, we're exponentially increasing the number of connections that are required for redundancy. And it looks relatively confusing, and those are all layer 3 links. It's a lot of subnets, a lot of routing. But if we take that same design and we apply a core, you can see how much less complex that network design becomes. So there's a trade-off, right? There's a trade-off between the cost of the core itself, the implementation and management of the core, versus the complexity and management of all of those separate redundant connections for our full mesh connectivity that we would have if we didn't have the core. So there's a significant difference between those, right? Very, very important. They describe, the number of links that would be required and so on. It is an exponential value. As you add an additional distribution layer switch, you're significantly increasing the number of connections that you would have to have. So it really depends on multiple factors, as we see right here. It depends on multiple factors, you may start off with a design that doesn't necessarily require a core. But you may end up adding one later on because you're adding more campus nodes, if you will, to the topology. And it may just become required at that point based on the density of the network that you have. So it depends if it's a high density, large campus design, or a medium density or a small density. Like I said, some cases in a small campus design, you might not need any of the 3 layers. It might just be one switch, one physical switch, or at least the switch stack, and it's providing all of those services in one physical component. At which layer of the campus layered model is PoE typically used? Of course, that's going to be the access layer. I would say there is a possibility, of course, of having PoE at the distribution layer, but generally it's going to be the access layer because that's where your APs are going to be attached, that's where your security cameras are going to be attached, and so on. But again,
so Scott,
yeah,
Scott, so I actually have a real world application for you there. We actually do our distribution for access points at our access points are actually on our distribution layer instead of the access.
Okay.
Because we don't always buy PoE switches for the access that can do the new throughputs.
Got
So
it.
a lot of the new access points, like the 3802s, require 30 megahertz, and a lot of our switches are not PoE plus, so we couldn't actually have the access switch provide the power to those devices.
Got it. Yeah, you're not getting the AT power standard at the access layer. Yeah, you're getting the pre AT power standard. So you're not getting the 30 milliwatts. You're only getting the 15.4 milliwatts or whatever that you're going or 15.4 watts. Sorry, not milliwatts. That would be very, very low power. But yeah, that's interesting. Well, and again, that's what I was kind of talking about in the beginning of this, right? This is not this traditional core distribution access design is not set in stone, right? This is not something. This is a recommendation, and there are always going to be exceptions to the rule, right? Depending on how you decide to implement your overall design. But certainly for the exam purposes and for just kind of general design guidelines, the 3-layer model is a pretty good start, if you will. What is another name for the core layer? That would be your backbone, right? Because that's essentially what it's providing. It's providing high-speed backbone routing to get from point A to point B. That's the whole point of that particular layer. All right. So the last section we'll talk about is the campus distribution layer design. There are 3 distribution layer design models: traditional distribution layer, simplified distribution layer, and software-defined access design, which, by the way, is incorporates the first 2 potentially. We'll see that as we kind of go through this discussion here. Traditional LAN designs, we have the 2-tiered approach or a multi-tiered approach at least, right? Possibly 3 tiers. But there's always going to be some sort of segmentation between our layer 2 access and our layer 3 access. And again, traditionally the layer 3 boundary is going to be at the distribution layer. The layer 2 boundary is going to be at the access layer. All right? But in order to be able to facilitate this design and to incorporate the redundancy, we have to have physical redundancy to the distribution layer. But that introduces design challenges in and of itself, because now we've got loops in our layer 2 topology that are going to cause some serious issues unless we manage them with some sort of loop avoidance mechanism like spanning tree. All right? So it says here, it's recommended that you restrict a layer 2 VLAN to a single wiring closet or an access uplink pair to eliminate topology loops that spanning tree must block. So they're saying, in essence, let's go ahead and design out spanning tree, even though we'll never get rid of it completely. Let's go ahead and design out spanning tree and make sure that we are limiting a particular VLAN to a particular closet. So you look at the diagram here, that's more of kind of your traditional design. VLAN 30 only goes to the switch on the left. VLAN 40 only goes to the switch on the right. And we have a layer 3 link between the distribution layers. So we've designed out the loop in this design, right? Layer 3 routed links do not span the VLAN. So we route the traffic, we don't switch the traffic. So in this particular design, we're not as concerned about implementing spanning tree. It's mostly implemented, it's always implemented. You never get rid of spanning tree, but it's mostly implemented in this case for if somebody mistakenly connects a wrong port to another port or creates a loop inadvertently, as opposed to as part of the design, right? The problem with this, and VLAN 30, by the way, could be the voice VLAN, and VLAN 40 could be a voice VLAN. So now we've got essentially layer 3 to the edge, right? That's what we're talking about here. Let's see what else they say here. Restricting a VLAN to a single switch provides a loop-free design, but it does limit network flexibility. To recreate a resilient IP gateway for VLANs in the traditional design, you must use first hop redundancy protocols, which provides hosts with a consistent MAC address and IP gateway. So again, let's talk about what they're saying there. They're saying, okay, we've designed out this layer 2 loop in our design, but now we have two distribution layer switches that can act as default gateways for that particular VLAN. So the switch on the left could act as the default gateway for VLAN 30. The switch on the right could act as the default gateway for VLAN 40. And what we would want them, if the switch on the right fails, we'd want the switch on the left to be able to take over that routing role. All right. And that's when we get into our first hop redundancy protocol design, where we might be implementing HSRP. That's a Cisco proprietary redundancy protocol. VRRP, which is very, very similar to HSRP. Some slight differences in the MAC address that it uses and the multicast address it uses and so on. Overall, though, pretty similar in design, but it's the open standard version. And then we have GLBP, which is our first hop redundancy protocol that allows us to do load balancing to utilize all the links at the same time. But these are considerations that you would have to take into account if you have this design. And we'll get into these technologies a little bit later on. We'll talk about the configurations. We'll actually do some labs with these different configurations a little bit later on. All right. Now, a loop design is where you have essentially the VLANs that span across multiple switches. So VLAN 30 exists in the entire enterprise or the entire campus, if you will. And in that case, a user could move from VLAN 30 in one switch to VLAN 30 in another switch. Their attachment doesn't really change because they're staying within the same subnet. They can have the same policies applied and so on. Whereas the loop-free design, if I move from switch A to switch B at the access layer, I'm actually changing my layer 3 attachment into a different broadcast domain completely. Something to consider. This is more of a traditional loop design, but now you have to take into account everything is switched and not routed, and we have to get rid of those redundant paths. The primary protocol that we use to do that, of course, is the spanning tree protocol. That's going to, this switch on the left could still be the gateway for VLAN 30. We need to make sure that our spanning tree topology matches our first hop redundancy topology. So it gets a little bit more complicated. Secondarily, I should say, we need to make sure that the convergence timers, that the protocols themselves react the same way to a topology change. Oftentimes, the first hop redundancy protocol timers are completely different than your layer 2 loop avoidance mechanisms, right? Rapid spanning tree will converge in subseconds, whereas the default timers for, say, HSRP might be 10 seconds or so before convergence occurs. So that's, adds a level of complexity, if you will, to the design. All right. An alternate way that we can handle layer 2 access and avoid the complexity altogether is what we call a simplified distribution layer design. We take a lot of our physical switches and they act as a single logical switch. And this is where we do things like virtual switch stacking. If it's a couple of 6500s, and we can merge them together into one virtual switch over the network. Physical switch stacking with something like Stackwise technology, and so on. We talked about this would be something that would be more applicable to a smaller design, and you might not even have these separate switches down here. It might just be one large stack. We have a lot of customers that do that actually because they don't need the separate architectures, right? We can implement technologies like Ether channel. We'll talk about that with PAGP or LACP later on, the link aggregation control protocol or the port aggregation protocol, or no protocol at all if we want to do a static Ether channel, and so on. So all of these things are going to require some different design elements. The last thing that we talk about, of course, is what do we do with software-defined elements, right? Any kind of design, whether it's a layer 2 design or a layer 3 design, if it's a multi-tiered architecture design or a flat architecture design, we can incorporate some sort of software-defined access where we can enable what we call virtual network overlays on our physical network. So the overlay network is the software-defined piece, and the underlay network is the physical component piece, right? And we have what we call northbound APIs and southbound APIs that allow us to control the logical piece versus the physical piece. And we'll get into that later on when we actually get into the software-defined access piece. So it's interesting. We'll see that towards the end of this class. That's part of the self-study section, but like I said, I'll probably try to record some of those lessons as well. Which of the following issues can be a problem with redundant paths in a traditional distribution layer design with VLANs spanning multiple switches? That was the traditional loop topology, not the loop-free topology, and loops would be the answer to that question because the VLANs span multiple switches, which means we're going to have that redundancy, and spanning tree is something that we would have to incorporate in that case. All right. So the last thing we'll do in this section, we're going to do our little summary challenge here. These are kind of just questions that we cover at the end of each section as a kind of a review for what we talked about. Which of the following is used to manage the automation of network device configuration? Is it SD-WAN? Is it SD-Access, DNA Center, or vBond? Well, the actual platform is Cisco DNA Center. SD-Access and SD-WAN are specific software-defined components, but the overall platform is the DNA Center. How many layers are recommended in a hierarchical design? That would be a horrible question for the exam because it really depends, but we've traditionally talked about the core distribution and access layers. So that would be 3. An end user PC which should be connected to which layer? That is going to be the access layer. What layer provides our policy decisions? Filtering, security, QoS. That is our distribution layer. Which layer supports convergence for voice, wireless, and data? So this is also kind of a challenging question, right? Because, are they talking about physical connectivity or are they talking about policy, right? And I'm going to assume they're talking about physical connectivity, which would be access. So that's where our IP phones are going to be connected. Our PCs will then be connected to our phones. Traditionally, our access points would be connected to the access layer. And then our traditional PCs and data components would be connected to the access layer. Which statement about the network core design is true? It's a dedicated core layer allows the campus to be more easily accommodate growth. I suppose that could be true. From a scalability standpoint, where we saw the diagram without the core layer with the redundant distribution layer connectivity, and then we saw the diagram with the core layer, so there's a big difference there. The core layer is not really needed unless you have IP telephony. That's not true at all. A collapsed core is preferred in big networks. No, we would want a separate core. A collapsed core is preferred to a design where a distribution layer is moved down to the access layer. So that's not true either. Collapsed core means that the distribution layer and the core layer are combined together. So that would mean that A is our best choice here. And which is true, right? Especially when you talk about adding additional distribution nodes to the topology. Which layer should provide the highest switching speeds? Definitely the core, right? That's get traffic there as quickly as possible. Which of the following is used to manage the automation of network device configuration? Well, that seems to be repetitive. How many layers are recommended? 3. That's interesting. They're repeating the questions here. So it looks like we've already done these. PC should be connected to the access layer. What layer provides routing? That's the distribution layer. Which layer supports convergence for voice, wireless, and data? Access layer. Yeah, they're repeating all of these. Okay. So it looks like we've covered all these guys here. High-speed switching is the core. All right. So that concludes the first section. Let me go ahead and stop the recording. We'll see you guys in the next section.